In this last lecture of chapter 7, we're going to focus on a topic called power. And not only are we going to talk about the concept and calculation of power, we're also going to take this opportunity to remind everybody that physics is not all about just equations and derivation. It's all about it's also about the real world, which has numbers. And so anytime you see a real physical quantity such as force, such as mass, such as velocity and so on, not only do you want to know its definition and its formulas, you also want to know some typical magnitudes. So you have some idea. For example, we have this unit of force called Newton. Do you have an idea what Newton is, roughly speaking? How many pounds would that be? That's something you should know. Okay. By the way, 1 Newton is roughly 1/5 of a pound, or roughly speaking, 5 newtons make up about 1 pound. This can easily be found if you consider, a 1 kilogram mass, which weighs 2.2 pounds, which is also about 9.8 newtons because W equals mg, right? So that's just an example. So anytime you see a new quantity being defined, make sure you look at some typical magnitudes, okay? And this is what we're going to do for power. So what is the definition of power? As you can see here, power is the rate of doing work. Now we know how work is calculated, right? So power is dW dt by definition. Okay, so write that down. dW over dt. Now, if work is done with a force over displacement dr, then I can write dW as F dot dr, of course, right? That's dW. And you divide this by dt, okay? What is dr over dt anyway? That, of course, is velocity. So you can write F as power as F dot V. Okay, so if you exert a large force on an object, and as a result, the object moves at high speed along the direction of the force, then you're delivering a lot of power to it. And if F and V are perpendicular to each other, like when you do a uniform circular motion, okay, the velocity is tangential and the force is radial, so F dot V equals 0, then you're not delivering any power to the system. The centripetal force is not delivering any power, which means it cannot do any work, which means it cannot increase the kinetic energy. No wonder it is what's called uniform circular motion, because the speed cannot change as the kinetic energy cannot change. So that's a special case. Okay, so that's the definition. So just how fast work is done. Now, what is the unit of power? Anytime you see a new physical quantity, you want to pay attention to its unit. In the case of power, there are actually a number of different units being used. The SI unit for power is, if you break it down to fundamental units such as kilograms, meters, and seconds, we can see how we can do that. The unit of power would be that of force times velocity. Force, so that's Newton times meters per second. Now, Newton itself can be broken down into fundamental pieces. That's mass times acceleration, kilograms, meters per second squared. That is Newton, right? And you divide it by times another meter divided by another second. So it's kilograms meters squared over second to the power 3. That is the SI unit of power broken down into the 3 fundamental units, kilogram, meters, and second. But you know that's cumbersome, right? That's cumbersome. You don't want to, every time you see power, you write down kilogram, meter squared over second to the power 3. So how do we simplify that? Well, we have already seen how we accomplish that. That is by defining the unit after a physicist, namely the unit after a physicist. We don't use kilograms meters squared over second to the power 3. Rather, we call it a watt. 1 watt. Or W is defined as 1 kilogram meter squared over second to the power 3. Why do we use this name Watt? It is named after James Watt, the inventor of the steam engine, which of course delivers a lot of power at that time. So it makes sense, okay? You probably also know by now that the unit of energy, such as kinetic energy, which is Newton times meter, also has a different name associated with that. That's joule, okay? So 1 joule, Joule, that's named after another physicist, James Prescott Joule, or capital J for short, is defined as 1 Newton times meter. That's the amount, that is the SI unit of energy. So we can also write down 1 watt as 1 joule per second. So if you do 1 joule of work per second, then the power delivered by you is 1 watt. Now, is 1 watt a lot of power? Is that a very high rate of doing work? Well, not really. On a human scale, that's not much. If you look at an ant, of course, an ant cannot possibly produce 1 watt of power output. But for humans, that's not a big deal at all. And if you look at horses, okay, here's another commonly used unit when it comes to power. It's called horsepower. History tells us that really had to do with Watt himself, James Watt himself. Somebody asked him to design and build an engine which can replace a strong horse in the work of pulling up water from a well. And then this person found that his strongest horse can pull 550 pounds of weight over a vertical height of 1 foot over a time period of 1 second. By the way, that's quite a lot. I mean, right? 550 pounds. You lift it 1 foot over a time of only 1 second. That's quite a lot. And the rate at which work is done, given these numbers, is called horsepower. And if you convert, you convert foot to meters and this mass from 550 pounds, which actually is a force, to kilograms, using 1 kilogram of mass corresponds to 2.2 pounds of weight. And then you will find that 1 horsepower is roughly 756 watts, okay? It's approximate, and to four stick figures, it is 745.7 watts. So it's about 3/4 of a kilowatt. And that is another commonly used unit when it comes to power, especially, for example, you rate the power of engine of a car. It's got 100 horsepowers or 200 horsepowers, whatever. At least in this country, we typically use horsepowers. In other countries where SI units are widely used, they use kilowatts. And roughly speaking, 1 horsepower is about 3/4 of a kilowatt. Okay. Is that really the power of a horse? Does that mean humans cannot even come close to that? Well, in this sense, the term horsepower is a little misleading. In fact, an average human can do that as well, at least over short periods of time. So what I want to do is I want to give you some typical numbers when it comes to powers. Okay, starting from something rather, I'm ignore those really tiny cases where the power is really small, such as the power consumed by a small IC chip. Rather, I'm going to start with human scale and go to a bigger scale. You can actually see, an entire range of something that consumes very little power to something that consumes extremely large amount of power. But this is only a partial list. Okay, we're going to start with the lower end on this list. That's the human brain. How much power does the human brain consume on average? And it turns out it's about 20 watts. Okay, it's about 20 watts. So the human brain uses about 20 watts of power, and that is, it consumes about 20 joules of energy per second. It's like a 20-watt light bulb, Is that a lot of power? No, not at all. The human brain is a supercomputer, all right? It's just an incredibly fast supercomputer. You have no idea how much calculation it does every second, because most of the calculation is unconscious. We do not know that it's doing that. Our brain is doing that. For example, it's regulating our temperature, it's regulating our blood pressure. It does all kinds of things without our knowledge. Okay, the conscious part of the brain is a tiny portion of the brain power. So for such a supercomputer, using 20 watts is incredible. You got to compare with an artificially made supercomputer. Okay, a typical example of a recently made world-class supercomputer uses 4 million watts of energy, 4 megawatts. A mega is 10 to the 6 or a million. This one only uses 20 watts. Think about it. It's incredible. So, the human brain is one of the most efficient gadgets made by nature. And humans, the artificial devices, do not even come close to that kind of efficiency. What about the average power consumed by the entire human body? Now we're talking about a person in his or her normal state. Okay, you're not, running at the top of your, top of your speed. You're not screaming. You're not fighting with people. And then typically on an average, a 24-hour period, on average, you're consuming about 100 watts. That's a very easy number to remember, by the way. 100-watt light bulb. Okay, that is the typical energy, typical power humans consume, 100 watts. So we use about 100 joules per second, roughly, which is not a whole lot. But if you compare that with a horsepower, which is 746 watts, that's quite a lot less. Okay, and that's how much power a typical horse can deliver. But does that mean humans cannot do that? Well, it turns out we can, even though on average we only use 100 watts of energy, 100 watts of power. When we are under stress, when we have to perform, let's say you're running away from a bear, okay? At least for a few seconds, for a short burst, you can produce a peak power much greater than 1 horsepower. You can produce something like 2 kilowatts instead of 3/4 of a kilowatt, which is 1 horsepower. So we're looking at about 2 kilowatts or more. I mean, we're talking about 2 kilowatts. That's an average person. Not for a world-class sprinter like Usain Bolt. It's more than 2 kilowatts. But that only happens for a number of, for a short burst, like a few seconds. Okay. What is the peak power output of a typical car? Well, typical cars, we use horsepowers, right? Like 100 horsepowers, 200 horsepowers. So let's say, it's around, let's say around 150 horsepowers for a typical car. Not the fanciest one, but still, not terrible bad. 150 horsepowers. Each horsepower is roughly 750 watts. Okay, so you take 150 times 750, and you get roughly 100 kilowatts. Okay, so you compare with the maximum output of a human, you're looking at roughly 50 times as much. Okay, that's for a car. All right. Now, next, let's look at what's called solar constant. That's a big name, a solar constant. What is it? Well, the sun produces energy and it's intercepted on Earth. Suppose I hold a card of 1 meter by 1 meter in area in my hand, at the edge of the Earth's atmosphere. Okay, right here. Okay, you have a card of 1 meter by 1 meter in area facing the sun directly. How much power do you intercept from the sun? That is called a solar constant. And to 2 sig figures, it is about 1.4 kilowatts. So the intensity, which is the intercepted power divided by area, is 1.4 kilowatts per meter squared. That is known as the so-called solar constant. Okay, so this tells me roughly that if you go to the edge of the atmosphere and you face the sun with a interceptor of only 1 meter by 1 meter, which is not a whole lot, you will catch about 2 horsepowers. That's a lot, you think about it. Okay, now, a related concept, related number, a typical solar panel, okay, that you put on your rooftop. What kind of energy, what kind of power does it intercept? Does it produce, I would say? Well, there is an efficiency issue. That is, whatever energy it gets from the sun, it doesn't convert 100% of that energy into electricity. You know, there's an efficiency, and a typical efficiency is in the low teens, like 12%, 13%. Okay, so the typical amount of energy, power you can get, you know, that turns into electricity for a 1 meter by 1 meter size of solar panel on the surface of the Earth on a sunny day is only about 120 watts. Okay, so it's about, you know, 1 order of magnitude less than the raw energy you get from the sun. Okay, so that's solar panels. Now, what is the average power consumption of a typical American household? Well, you know, think about it. Okay, you have your microwave, you have your refrigerator, you have your TV, you have your ACs in the summer, which consumes a lot of energy. A typical AC unit can be several thousand watts, several kilowatts. But you know, it varies from season to season, from hour to hour, and so on. But typically, looking at, you know, maybe around 1 to 2 kilowatts. Okay, so typically the order of magnitude is 1 kilowatt. 1 kilowatt. All right. Some other countries, maybe this number will be a lot smaller. Well, one of the really biggest users of energy per capita. All right, now something bigger. The peak power output of a blue whale. Okay, any idea how much that is? Well, there's a number that I found, and that number is 2.5 megawatts. Megawatts, 2.5 million watts. You compare with the output of a car, which is 100,000 kilowatts. So we're looking at more than an order of magnitude higher. Okay, that's a blue whale. You compare that with the typical power of an old-fashioned locomotive. Which one is greater? Well, actually, they're very similar. The typical power output of an old-fashioned locomotive is about 3 megawatts. See how close it is? Okay, I mean, just even the sizes are similar, right? A blue whale and an old-fashioned train, it's about 3 megawatts. Okay, now comes something more modern. The GE90 engine. It is used to power a modern Boeing airplane like 777 or 787. In the old days, to cross the Atlantic or the Pacific, you need an engine. You need an airplane with 4 engines. You know, these jumbo passenger jets like 747, it's got 4 engines. The 777 and 787 only have 2 engines. It's because each engine is more powerful. Okay, the GE90 engine is a state-of-the-art piece of work, and it has a power output, maximum power output of about 75 megawatts. Wow, 75. That is a lot more than a blue whale. Okay, 75 megawatts. You compare that with the blue whale, which is 2.5 megawatts, right? Even a locomotive is nothing to compare with a modern GE jet engine. Now, what about a typical nuclear power plant? How much power does it produce? You know, the typical nuclear power plant can support the power usage for, you know, many thousands of households, and like an entire city, right? And the typical power output for a nuclear power plant is 1 gigawatt. 1 gigawatt, what's a giga? 10 to the 9. 10 to the 9 watts. You compare that with, you know, DE engine, which is 7.5 times 10 to the 7. Here is 10 to the 9. Okay, so it's different. This is greater. Now, going along the same path as electrical power plants, how about the world's largest hydraulic electric power plant, the Three Gorges Dam in central China? Okay, it is the world's largest hydraulic power plant and has a power output. Here's a picture of that. It's got a peak power output of 1.83 times 10 to the 10 watts. So it is 18.3 gigawatts. It's like, you know, almost 20 of those nuclear power plants together. Okay, and that is roughly 1/3 of the peak power consumption in the state of California or the entire country of Great Britain. Okay, so this one dam can produce enough electricity to support 1/3 of the state of California and 1/3 of the country of Britain at peak power consumption. Now, here is something even bigger. The total power consumption of the human world, okay? So, you know, humans we're only part of the Earth, but any power consumption related to human activities, like, you know, the ACs that we use, the car that we drive, you know, the airplanes that we fly, and, you know, all of these human activities added together. What kind of power consumption are we talking about here? We're talking about in 2019, by the way, okay, 1.91 times 10 to the 14 watts. Okay. So what is it? That's 191 trillion watts. Okay, 191 times 10 to 12 watts. You compare that with the power generated by the Three Gorges Dam, you'll find there's an order of magnitude, 4 orders of magnitude difference. So therefore, it takes a little over 10,000 of these Three Gorges dams to produce enough power to power the entire human race. And that's the year 2019. Okay, and by the way, this number is roughly 0.1% of the total power we intercept from the sun. The Earth, you know, intercepts a certain amount of energy from the sun, right? Certain amount of power from the sun. And this number is roughly 0.1%. So the human activities account for about 1/10 of the total energy we ever get from, you know, per second from the sun. It doesn't sound like a big number, but, you know, a lot of things that's not human related, we still need it. Yeah, it's still like the ocean, you know, temperature goes high and low, whatever, it all takes energy, and it all came from the sun. So the human activity should be only a very, very small part of it. Indeed, it is a small part of it. It's 0.1% of the total energy, total power we receive from the sun. Okay, so these are some typical numbers, and again, you can look for even more examples, especially in the microscopic world, you know, things that cost very little power. There's some interesting numbers as well. So I wish to use this opportunity to illustrate the point that you need to know some numbers. Okay, it's not just about equations and formulas. Now, before we end this lecture, let's look at a little estimation. Can you estimate the 0 to 60 miles per hour acceleration time for a typical car? Now, you know the number, right? For example, take a look at your car. How long does it take to go from 0 to 60? Well, the typical number is maybe 7 seconds, 8 seconds, 9 seconds, and so on, right? We're talking about typical car, not really fancy ones or slow ones, right? Can we get that number from estimation? Well, we're going to make things a little bit simpler. We're going to assume that when you step on the gas, you're using peak power output, which of course is not true. In reality, it doesn't stay at peak power output. But let's assume, for simplicity, that the moment you step on the gas, the car produces peak power, P, which is a constant, P. So after a time T, what is the total work done by the car? It's P times T, right? And if this work turns 100% into the kinetic energy of the car, by the way, that doesn't happen because, you always have energy loss due to friction of the wind, air resistance, and friction of the road, and you have, loss to heat and sound and so on. But, we're just only estimating, okay? We're only estimating. So let's say it's roughly converted to the energy of kinetic energy of the car is 1/2 mv squared. 1/2 mv squared, right? And we can find T now, okay? The time it takes to reach a certain speed is mv squared over 2p. No, you notice I did not use an equal sign, okay? So this symbol only means we're looking only at the order of magnitude. So let's look at some typical numbers, okay? The mass of a typical car. Mass of a typical car, we're looking at about 1,500 kilograms, give or take. 1,500 kilograms. I'm using prime SI unit. And the speed is 60 miles per hour, which when you convert to meters per second is roughly 27 meters per second. Okay, you square that, you divide it by 2p. A typical car, we're looking at maybe 150 horsepower, you know, not very strong, but not very weak. 150 horsepower, each horsepower, as you know, is 746 watts. Okay, remember you have to turn everything into prime SI unit. Okay, and if you do this calculation, you find a time to be in two figures, 4.7 seconds. Okay, now, can your car do that? Can your car reach 60 miles per hour in 4.7 seconds? Well, I don't know about you, mine cannot do that, okay? Most cars cannot do that. Most cars, like I said, you know, reach 60 miles per hour in about, you know, 7, 8, 9, or maybe 10 seconds. So this is roughly half of the real world result, which makes sense because we have ignored air friction. We have assumed 100% conversion of power to kinetic energy. Okay, there's a, you know, that's an ideal where we also assume that throughout the entire acceleration, the car maintains peak power output, which is not true either. So it's no wonder we're getting a time that's shorter than what happens in the real world. The real world time is about twice as long, which makes sense. So even though it's not you know, a reproduction of the real world number, it is half of that, but that actually makes a lot of sense. Okay, so we get the correct order of magnitude, and indeed this t is less than what happens in the real world. If you get t equal to 20 seconds, in the real world it actually happens in 10 seconds, then something's wrong, you know? Okay, so that is our discussion of power. This also rounds up the lectures for chapter 7. And in the next chapter, we'll continue with our study of energy. We'll introduce a new form of energy called potential energy. That's chapter 8.